Hello all, and today we shall continue with our discussion on operational research. The problem that we'll be studying today is known as linear programming problem, and the method that we shall be studying today is known as a graphical method. So first, just let's understand that what is a linear programming problem. See, let's just look at the objective function here. It is maximize 6x1 plus 5x2. And here we are having two variables x1 and x2, and both these variables have been raised to the power 1. That means this objective function is a linear function. Similarly, be it this constraint or this constraint or this constraint, in any of these three constraints we are having variables x1 and x2 raised to the power 1. That's why all these constraints are also linear expressions. So we can safely conclude that all the mathematical expressions that have been considered in this particular example are linear in nature, and such a programming problem is known as linear programming problem. Why is it known as programming problem? Because they would be solved using some algorithms, because operational research subject is all about algorithms, and they would be solved using those algorithms which are very much efficient in solving such a set of expressions which are linear in nature. That's why this type of programming problems are known as linear programming problem. Now when I say linear programming problem, I do not necessarily mean that they have to be solved using some computer language. Of course, that can be solved using any computer programming language like Python or Java or MATLAB or Skylab, any such thing. But here we would be in this particular lecture would be focusing mainly on how to solve this problem using graphical method and without using any computers. See, for that, let's say that we are having two axes here, such that along this axis we are plotting x1, and along this axis we are plotting x2, as x1 and x2 are two variables here. Now first of all, let's consider this particular expression, and in this particular mathematical expression, which is a constraint, remember for solving any such a programming problem, linear programming problem, which is also known as LPP for short. LPP means linear programming problem in short. The first thing that we need to consider is one constraint function. So the first constraint function is x1 plus x2 less than or equal to 5, which can also be written as x1 plus x2 equal to 5. See, I am not violating this particular constraint here, because it says it is less than or equal to 5. Now when it is less than or equal to 5, it means it does include that equal to portion. So that's what we are considering here. So if we just consider x1 to be equal to 0, then the value of x2 which satisfies this x1 plus x2 equal to 5, this particular constraint function would be x2 equal to 5. Similarly, if we consider x2 equal to 0, then the value of x1 which satisfies this particular constraint is x1 equal to 5. So these two values or these 2 points 0, 5, 0, 5 and 5, 0, both these points, they satisfy this constraint. Now why do we need these 2 points? Let's see. If we just put 0, 5 here, then see, let's just say that each of these division corresponds to one numerical value. So first plot this 0 comma 5, then it would be in x direction we need to move 0 point, that is we would be focusing mainly on this origin. Okay, then 5 point would be 5 value would be 1 2 3 4 5. So, let's just okay, fine, 1 2 3 4 5, 5. So this point it represents 0 comma 5, this point, and if we plot 5 comma 0, then we would have 1 2 3 4 5, that is this point, it represents 5 comma 0. Now we have these 2 points which satisfies this particular constraint here. So what we would be doing is that we would draw a straight line through these 2 points. Now once we have drawn this straight line, then see this equal to condition, it is the extreme condition for this particular constraint, but other than that most of the values would be such that this less than part is there. So let's just identify one value which satisfies this condition as well, that is less than, and that can be, let's say if we take x1 equal to 1 and x2 equal to, let's say 3, then what does that do for us? If we just substitute the values x1 equal to 1 here and x2 equal to 3, then we are getting 1 plus 3 equal to 4, and which is less than 5. So this particular point, that is 1 comma 3, this one also satisfies this particular constraint. And now let's plot this value 1 comma 3. So see, it would be 1 here, then 1 2 3, there is this point. So this particular point, it represents 1 comma 3. Now this 1 comma 3, it satisfies the less than condition, and it is lying on this side of the line. So the region which we would be considering, which is bounded by this function, this line which is associated with this constraint, and the two this axis is this region. Why this region? I am just repeating myself, because this point which satisfies this condition x1 plus x2 less than 5 is lying on this side of the line. Okay, or we can further iterate it by considering one more point. Let's say we have point 2 comma 2, 2 plus 2, there is a, if the value of x1 is 2 and the value of x2 is 2, x1 is 2 and the value of x2 is also 2, then see 2 plus 2 is equal to 4, and 4 is less than 5, and let's plot this 2 comma 2 here. We have 1 2, then 1 2. So this point is also satisfying this less than condition, and it is lying on this side of the line. That's why we will be considering this region of the quadrant, then, or of the coordinate space. Then let's come to this constraint. Let me just rub this space so that I can have more blank space available to myself for further calculations. Okay, so now we would be considering this constraint. See, in this constraint we are having thrice x1 plus twice x2 less than or equal to 12, and here we are taking this particular condition. I mean, this is the constraint here, but out of that, the condition that we are considering right now is thrice x1 plus twice x2 equal to 12. Why equal to? Because this sign is there, which says that this left hand side is either less than or equal to right hand side. So for the beginning we are considering this equal to portion. Okay, now let's find out 2 points which satisfies this particular condition. There is thrice x1 plus twice x2 equal to 12. If we consider x1 equal to 0, then x2 equal to 6 would satisfy this condition. Similarly, if we consider x2 equal to 0, then x1 equal to 4 would also satisfy this particular this particular problem. Therefore, or this particular equation, therefore we would have two such values, two such points which are satisfying this constraint. Those are 0, 6 and 4, 0. Now let's plot 0, 6. 0, 1, 2, 3, 4, 5, 6. So we are having one value here or 1 point here, and then we are having 4, 0. 1, 2, 3, 4. Okay, so this point. So we are having two values here, the 2 points here, and then we would join it, and now we would find out that which region of this line we will be considering for further calculation. See, let's just choose any point which is simple to calculate. Let's consider 1, 1. See, if we put x1 equal to 1 and x2 equal to 1, then in this one it becomes 3 plus 2. So 3 plus 2 is equal to 5, and 5 is less than 12. Okay, so this 1, 1 point, it satisfies this particular condition. And on which side of this line does this point 1, 1 lie? See, 1, 1. Okay, so this point is lying here, so we are considering this point, and this point is lying once again on this side of the problem. Okay, that's why what we would do is that we would once again consider this region. Now see, why have we considered only this first quadrant and not this entire xy coordinate system? That's because this particular condition is there, that is x1 plus x1 x2 greater than or equal to 0. That is be it any value of x1 or x2, they always have to be either greater than 0 or equal to 0. That means this quadrant, this quadrant where we are having negative x1, that is not considered, or this quadrant where we are having both negative x1 and negative x2 value, that also cannot be considered. Similarly, this quadrant also cannot be considered because here we are having negative x2 value and plus x1 value. So if even one value is or one variable is having negative value, then we cannot consider any particular quadrant in this Cartesian coordinate system. That's why what we have considered is a positive quadrant or the first quadrant of the coordinate system, where both the x1 x2 are ensured to be positive. Okay, fine. Now see, this out of this particular region or this problem, let's find out which region is common to both, or which are the points which are common to this whole problem. See, this is one point which is common to this this entire system of expressions. Similarly, this one is another such point which is also common to this entire set of expressions. This is another point which is common to this entire expression set of expressions, and this point is also common to this entire set of expressions. Now one might ask that why these points are only considered to be common points. That's because, let me just go back a little bit. Yeah, see, we sorry can draw the region which is common to we can draw the region which satisfies all these constraints, and that would be this particular region. Okay, that is this region. This region is common to both the shaded regions, and this is the region which definitely satisfies all the constraints, because this, see, this region, it satisfies only the second constraint. This part of the region, it satisfies only the first constraint, but this is the region which satisfies all the constraints. Now in this common region, which are the corner points that is of our prime importance? This point, this point, this point, and this point. So this point is definitely 0, 0. Then this point is 0, 1, 2, 3, 4, 5. Yeah, 0, 5. Similarly, this point is, just a minute, one, 2, 3, 4, 4, 0, and this point would be approximately 2 comma 3. Okay, now see, let's find out that what is the value of the objective function for each of these corner points. So for the first corner point, let me just rub these things. Okay, for the first corner point, see, the value of objective function is 6 into 0 plus 5 into 0, which is equal to 0. Fine. For the second constraint, for the second corner point, what would be the value? 6 into 0 plus 5 into 5, that would be equal to 25. For the third corner point, what would be the value of the objective function? That would be 6 into 4 plus 5 into 0, which is equal to 24. And for the last corner point, that is 2 comma 3, what would be the value of the objective function? That would be equal to 6 into 2 plus 5 into 3, that would be equal to 6 to the 12 plus 5 to the 15 equal to 27. So in this case, see, this is the value which is having maximum this is the point which gives us the maximum value of the objective function. So this is the point which should be considered for our further conclusions. Why? Because in this particular problem, that was our objective. Our objective was to maximize the objective function, and what is the maximum value of the objective function we are getting? That is equal to this 25. And when are we getting this 27 value? When we are considering this particular point. So this particular point, it represents the solution here, and that would be x1 equal to 2 and x2 equal to 3. This is the solution of this particular problem, and that is how we solve a problem using graphical method in linear programming problem. Thank you.